take a second and just notice your own brain right now. You're listening to my voice, and in doing so, you are effortlessly filtering out the ambient hum of your room. You're ignoring the feeling of your clothes against your skin.
Right, the background noise outside your window.
And exactly. You aren't processing all of those sensory inputs equally. You're dynamically allocating your cognitive resources to a single specific stream of information. And it's a biological superpower. We call it selective attention.
And the ability to dynamically focus on the right information at the exact right time is arguably one of the most profound concepts we've ever borrowed from human biology and ported over to artificial intelligence.
Yeah.
It's something we take entirely for granted until we actually sit down and try to teach a machine how to do it.
And that is exactly our mission for this deep dive. We are exploring a really fascinating source text titled Attention, the Breakthrough, which covers the foundational architecture of modern AI.
It really is the foundation.
Yeah, we're going to look at how giving this human superpower of selective focus to machines solved a massive systemic bottleneck in deep learning. If you're a software engineer, a systems architect, or just someone obsessed with how complex data pipelines are optimized, this is the exact moment where the modern AI revolution truly begins.
To really appreciate the magnitude of the breakthrough, we have to look closely at the problem it was trying to solve.
Right.
Because before attention mechanisms existed, the dominant architecture for translating sequences like feeding in an English sentence and getting a French sentence out was the C2-sec model.
Yeah.
And had a glaring Achilles heel.
The bottleneck problem.
Yeah.
I was reading through the source material, and it details how these early models used an encoder-decoder structure. The encoder's job was to read an entire input sentence, regardless of whether it was a quick 5-word greeting or a dense, 50-word legal paragraph. It was forced to compress all of that meaning, syntax, nuance, and context into a single fixed-size vector.
A single mathematical representation.
Right. And then it handed that one vector over to the decoder, which had to magically unpack it and generate the translated sentence word by word.
The source material uses a brilliant analogy for this that I think really highlights the absurdity of the approach.
Oh, the symphony one.
Yeah, the symphony analogy. Imagine taking a massive, complex, hour-long symphony, compressing all of those instruments and movements into a single dense chord.
Just one chord.
And then asking a musician to reconstruct the entire symphony just by listening to that one chord.
I mean, it might work for a tiny 3-note jingle.
Right, you can compress Mary Had a Little Lamb and reconstruct it. But for a whole symphony, you lose the nuances, the timing, the critical contextual details.
Right, and in the context of early AI, this meant that once an input sentence went beyond, say, 20 or 30 words, the performance just fell off a cliff.
The memory was just too squished.
Yeah. If you look at the early iterations of commercial translation tools, this is exactly why they struggled so much with long paragraphs. The system would start out strong on the first few translated words and then rapidly degrade into absolute gibberish.
Because the fixed-size vector simply ran out of capacity to hold the information from the end of the original sentence.
Okay, let's unpack this. How did we get past that bottleneck?
The paradigm shifted in September 2014. A team of researchers, Dmitry Bodanov, Kyunghyun Cho, and Yoshua Bengio, published a paper.
Oh, right.
And it had a very understated academic title, Neural Machine Translation by Jointly Learning to Align and Translate.
Very flashy.
Right. Didn't have flashy marketing, but the core idea inside was a seismic shock to the field of deep learning. They looked at the sec-to-sec model and realized the encoder was actually doing a massive amount of valuable work that was systematically being thrown in the trash.
Because the encoder wasn't just generating that final compressed vector. It was doing work at every single step of the sentence.
Exactly. As the encoder processes an input sentence, it produces an intermediate hidden state at every single time step.
Okay.
It generates a state for the first word that updates and generates a state for the second, a state for the third, and so on. Each of these hidden states captures a snapshot of the sentence's meaning up to that specific temporal point.
But in the old rigid architecture,
all of those rich, position-specific intermediate states were simply discarded. They were written into memory, used for the next step, and overwritten. Only the very final state, that overloaded single chord, was kept and passed to the decoder.
So Badanda's team basically asked a remarkably simple question. What if we just stop throwing them away?
Yeah, what if we keep all of those intermediate states and give them to the decoder?
It's disarmingly simple in retrospect, but computationally, I imagine that introduces a new problem.
It does. You can't just dump 50 complex, vectors onto the decoder all at once and expect it to make sense of the noise. You need a routing mechanism to manage it. So they proposed that at each step of generating an output word, the decoder computes a relevance score. It actively looks at all those preserved encoder states and decides dynamically which ones are most relevant to the specific word it is trying to generate right now.
The source compares us to two different ways of taking an exam, which I think perfectly illustrates the shift. The old C2-SIC approach is essentially a closed book exam.
Yeah.
The model reads the input, closes the book, compresses all the information into its working memory, and has to write the translation entirely from that one compressed memory vector.
But attention turns it into an open book exam.
Exactly. The decoder can look back at any page, any specific hidden state of the encoder while it's answering the question. It still needs to know what it's looking for, but it no longer has to rely on a single crammed memory vector.
What's fascinating here is the immediate empirical result this had on performance. The improvement in translation quality wasn't just a minor incremental bump. It fundamentally changed the scaling laws of the models.
Because it wasn't bottlenecked anymore.
Exactly. Because the total information available to the decoder now scaled naturally and proportionally with the length of the input sentence, the performance degradation curve for long sentences completely flattened out.
Wow.
Where the old models would fall apart at 20 words, this new attention-based model could maintain high-quality, coherent translations at 50, 60, or even 70 words. It proved conclusively that the fixed size vector was indeed the absolute bottleneck holding the field back, and attention was the cure.
So, mechanically speaking, how does this model actually search through its open book?
Oh.
The field's standardized around 3 specific terms to describe this process, and if you're building or working with any modern architecture today, these are the atomic units of your daily life: queries, keys, and values.
Yes, Q, K, and V.
I love the library analogy the source uses to make these abstract vectors a bit more concrete. Let's walk through that. Imagine you are standing in a massive, sprawling library. You have a specific goal in mind. You want to know what caused the fall of the Roman Empire. That question, your specific intent, is the query. In the context of our AI decoder, how does the query actually manifest?
The query is the decoder's current hidden state. It is essentially the network asking a mathematical question. Based on the French sentence I have generated so far, what English word should I output next?
Okay, so now you're in this massive library and you're surrounded by thousands of books. You obviously don't have the time or the compute power to read every single page of every single book to find your answer.
No.
So you walk down the aisles and you look at the titles and the brief descriptions printed on the spines of the books. Those spines are the keys. In the AI, what are the keys representing?
The keys are the encoder's hidden states. They serve as rich, dense summaries of each input position. They're the metadata that the query is going to evaluate.
Right, and the actual text inside the book, the granular historical data you want to extract, that's the value.
Exactly.
So you have your query, which is your question, your keys, the book spines, and your values, the actual content. The attention process executes this retrieval in 4 distinct steps. Step 1, you compare your query to every single key. You walk the shelf. Ancient Rome, a history, very relevant. Gardening in small spaces.
Completely irrelevant.
Exactly. How does the model actually compute those relevant scores in step 2?
How well the query matches each key depends on the specific architecture. But in Bodenau's original 2014 paper, this matching was calculated by passing the query and the key through a small, single hidden layer feed-forward neural network.
Okay.
It took those 2 vectors as inputs and spat out a raw, unnormalized score indicating their compatibility.
Step 3 seems crucial for making the math actually work, normalizing those raw scores. The source mentions passing them through a softmax function. For the engineers listening who might be deep in back-end systems but newer to machine learning math, how does the softmax function actually handle these scores?
Softmax is an elegant mathematical operation that takes a vector of arbitrary real numbers, which could be wildly negative or massively positive, and squashes them into a clean probability distribution.
So it forces a budget.
Yes, the outputs are always non-negative numbers that add up perfectly to 1.0. So now, our library search results are strictly quantified. The book on ancient Rome might get a weight of 0.45. A book on the broader decline of empires gets 0.35. A few others get tiny fractions, and the gardening book gets mathematically pushed down to effectively a flat 0.
Which brings us to step 4. Computing the weighted sum. You don't just pick the single highest scoring book and ignore the rest entirely.
Right.
You combine the values, the contents of the books, multiplying them by their softmax weights. You extract 45% of your information from the Rome book, 35% from the Empire's book, and blend them together.
It creates a composite.
Yeah, the result is a highly context-aware, customized summary vector that is perfectly tailored to your original query. You feed that weighted combination into the decoder, and it uses that precise context to generate the next word.
And this specific mechanism of blending the outputs, rather than selecting just one, represents a massive technical fork in the road in early AI development. It was the choice between soft attention and hard attention.
Here's where it gets really interesting, because the idea of blending those inputs has massive implications for how these models are actually trained on hardware.
Oh, absolutely.
Let's contrast the two approaches. Think of soft attention like a giant audio mixing board in a recording studio. You have continuous sliders for every single channel. You can push the drums up to 80%, keep the bass at 40%, and drop the rhythm guitar down to 2%. Everything is blended smoothly.
Right.
Hard attention, on the other hand, replaces those continuous sliders with binary light switches. A channel is either 100% on or it's 100% off. You make a discrete choice, attend to this exact word, completely ignore all the others.
Which is intuitive.
Yeah, intuitively, hard attention feels much more like human biological focus. When you look at a coffee cup on your desk, your eyes fixate on the cup. You aren't typically giving 30% of your visual processing to the cup and 70% to your monitor in a blended visual smear. So why did soft attention win out so completely in the software engineering world?
Soft attention won because of one fundamental requirement in modern deep learning: differentiability.
The magic word.
It really is. Soft attention relies on continuous, smooth mathematical functions. If a function is continuous and differentiable, you can calculate its gradients. And if you can calculate gradients, you can train the entire massive system end-to-end using standard gradient descent and backpropagation.
You just follow the slope.
Exactly. You can optimize millions or billions of weights directly and efficiently because the calculus gives you a clear mathematical path showing exactly how to adjust every parameter to reduce your error.
Whereas hard attention, with its binary discrete light switches, completely breaks that gradient chain. It's mathematically non-differentiable. You can't compute a smooth gradient across a sudden binary jump.
To train a hard attention model, engineers had to abandon standard backpropagation and rely on techniques from reinforcement learning, specifically things like the reinforced algorithm.
Oh, wow.
And for any software engineer who spent time in the trenches with reinforcement learning, you know the headaches involved. The gradients in reinforced estimators have incredibly high variance. The training becomes incredibly noisy, highly unstable, and painfully slow to converge.
Sounds like a nightmare to debug.
It is. You're essentially relying on trial and error with sparse rewards rather than following a smooth geometric slope down to your optimal solution. The trainability advantages and sheer stability of soft attention far outweigh the theoretical elegance and inference time efficiency of hard attention.
Makes sense.
So today, when the industry talks about attention mechanisms, 99 times out of 100, they are talking about differentiable, continuous, soft attention.
The beautiful byproduct of that differentiable soft attention architecture is that suddenly researchers had a window into the black box. Because we are mathematically generating a matrix of weights, a grid showing exactly how much attention the decoder is paying to every single input word at every single generation step, we could actually visualize the AI's thought process.
These attention matrices were an absolute revelation for interpretability. You can literally plot them on a heat map. The rows represent the generated output words, the columns represent the input words, and the brightness of the intersecting cell shows the exact attention weight.
The source text brings up a classic example that really drives this home. Translating the simple English phrase, "the cat sat on the mat," into the French, "le chat s'est assis sur le tapis."
Classic.
If you look at the matrix, when the model generates the French word chat, the cell corresponding to the English word cat glows brightly. It's focusing heavily on the right semantic translation.
Which is exactly what you'd hope to see.
Right. But it gets even better when you look at structural differences. French and English have different word orders for certain phrases, especially with adjectives and nouns. Think about the green apple versus la pomme verte.
Right. Adjective flips.
When you visualize the translation of those phrases, you actually see the bright spots in the attention matrix naturally cross over each other. The model learned completely on its own, purely from the data, and without any hard-coded grammar rules, how to map and reorder syntax between two entirely different linguistic structures.
It is a profound thing to see plotted on a screen. For the first time, software engineers weren't just staring at a loss curve dropping on a terminal output. They were looking at a geometric representation of something that looked remarkably like linguistic understanding.
Yeah.
However, as engineers, we have to inject a necessary analytical constraint here regarding what we're actually seeing.
Ah, the interpretability caveat. We can't get too carried away.
We have to be incredibly careful not to anthropomorphize these heat maps. An attention weight matrix displays correlation. It does not definitively prove causation.
Okay.
It shows us exactly what mathematical vectors the model is looking at during a specific step, but it doesn't tell us what the model is thinking or how it's transforming those features internally.
Because it's still a massive neural network doing other transformations.
Exactly. Subsequent research in the years following this breakthrough revealed that highly weighted attention heads do not always perfectly align with actual feature importance when you do rigorous ablation studies. But as a high-level diagnostic tool and a way to build human intuition about a model's behavior, visualizing attention was an absolute game changer.
Let's pivot and talk about the hardware implications, because the evolution of attention didn't stop with Bodenau in 2014. We mentioned earlier that Bodenau used what we call additive attention. To compare the query and the key, he concatenated them and fed them through a small neural network hidden layer. It worked brilliantly for accuracy, but then in 2015, a researcher named Minthang Luong proposed an alternative: multiplicative attention, also widely known as dot product attention. For an audience deeply familiar with system optimization, what's the fundamental difference in how these two approaches utilize hardware?
This is where hardware architects really get to take a victory lap. Additive attention involves concatenating vectors, loading weights, and passing them through a feed-forward layer. In hardware terms, that means sequential operations, heavy memory bandwidth utilization, and operations that act somewhat like complex CPU branching.
Not ideal for scaling.
No, not at all. Luong realized that instead of passing the query and the key through a neural network to find their compatibility, you could bypass that entirely by just calculating their dot product in vector space.
Because if the query vector and the key vector are pointing the exact same direction in that high-dimensional space, their dot product is a large positive number, meaning they're highly relevant. If they're orthogonal, pointing at right angles, the dot product is 0, meaning no relevance. It replaces a complex compatibility evaluation with raw, vectorized math.
The hardware advantage of that shift is monumental. Calculating dot products across massive sets of vectors is simply matrix multiplication. And GPU's graphics processing units are designed from the silicon up to do highly parallelized matrix multiplication better than anything else on the planet.
They just chew through it.
Exactly. Additive attention choked on sequential operations. Dot product attention replaced it with a pure mathematical operation that could be blasted across thousands of GPU tensor cores simultaneously. It shifted the bottleneck from complex logic back to raw FLOPs, which made training these models exponentially faster.
But reading through the source, it's clear nothing is ever perfectly easy in deep learning. As researchers scaled up these models using dot product attention, they ran into a very subtle mathematical bug. Something about the model getting too confident. What exactly was happening mathematically as the dimensions of these vectors got larger?
The problem arises from the behavior of vector math at high dimensions, combined with the softmax function we talked about earlier. As models became more sophisticated, the dimensions of the query and key vectors expanded up to 512 dimensions or more.
Right.
When you take the dot product of two vectors with a very high number of independent dimensions, the resulting scalar value tends to grow extremely large. The variance of the dot product increases proportionally with the dimension size.
And we have to feed those large scores back into the softmax function to turn them into our probabilities.
That is where the system breaks down. Softmax is highly sensitive to large numbers. If you feed very large numbers into a softmax function, the output becomes extremely peaked. The highest value gets pushed to 0.999, everything else is shoved down to effectively 0.
So it puts all its eggs in one basket.
The model becomes hyper-confident in a single answer. But more critically for training, when softmax gets that peaked, it hits the flat regions of the curve. The derivative of those flat regions approaches 0. This causes the gradients the crucial signals use to update the model during backpropagation to vanish.
The vanishing gradient problem.
They become so infinitesimally small that the network's weights stop updating. Learning completely halts.
The fix for this is famously elegant. It's called scaled dot product attention. How did they solve the vanishing gradient problem without losing the incredible GPU parallelization speeds of the dot product?
They introduced a mathematically simple scaling factor. The exact formula became the softmax of Q times K transpose, divide by the square root of dk, all multiplied by V.
So you just divide the dot product.
You take the dot product of the query and key matrices, but before you pass it to softmax, you divide it by the square root of the key dimension, which is that dk term. If your dimension is 512, you divide the dot product by roughly 22.6. That's it. That simple division drags those massive dot product values back down into a reasonable range. It prevents the softmax from saturating, keeps the gradients flowing beautifully during backpropagation, and allows the GPU matrix multiplications to sing without breaking the learning process.
If we connect this to the bigger picture, that specific formula, scaled dot product attention, is the atomic building block of everything that follows in modern AI.
It truly is.
But to truly unlock its power, researchers had to give the network the ability to hold multiple perspectives at once. Enter multi-headed attention. Think about going out to a restaurant. When you evaluate the experience, you don't just assign it one single global score in your head.
No, of course not.
You're running parallel evaluations. One part of your brain is attending to the flavor of the food. Another is judging the ambient lighting and the music. Another is calculating the value for the money. And another is rating the friendliness of the waiter. You have multiple attention heads analyzing different subspaces of the experience simultaneously.
In 2017, a team led by Ashish Vaswani formalized this exact concept for neural networks. Instead of executing one single attention function across the entire massive input vector, they systematically split it.
Right.
If you have a 512-dimensional vector representing a word, you don't do one massive 512-dimensional attention calculation. You split that vector into, say, 8 distinct heads, each dealing with 64 dimensions.
And each of those 64-dimensional heads gets its own independently learned query, key, and value projections, running entirely in parallel across the GPU.
Because they learn independently, they naturally specialize during the training process. One attention head might learn to strictly follow syntactic rules, tracking subject-verb agreement across a long paragraph.
Right.
Another head might focus entirely on semantic meaning, linking loose synonyms together. A third head might attend purely to positional proximity, looking at words that are physically close to each other in the sentence. They calculate all these different nuanced relationships simultaneously in parallel and then concatenate the results back together to form a deeply rich representation.
This represents a massive paradigm shift in computer science architecture. Before attention mechanisms, neural networks were dominated by fixed architecture processing. Data flowed through a rigid, predetermined pipeline, step by step, and every single input was subjected to the exact same geometric transformations regardless of its content.
Attention introduced true data-dependent computation, the actual pathways of information flow, the critical decisions about what gets multiplied by what, change dynamically at runtime based on the input data itself. The network actively decides in real time what matters and what to ignore, routing information to where it is needed most.
So what does this all mean? We have this incredible mechanism. We fix the C2 set context bottleneck. We have models that can dynamically focus on what is relevant, process it at blinding speeds on GPUs with scaled dot products, and evaluate multiple complex contexts in parallel with multi-head attention. We solved it, right?
We solved a massive piece of the puzzle, but there was still a lingering fundamental limitation dragging the entire system down. Despite all this brilliant optimized attention architecture, these models were still ultimately tethered to recurrent neural networks, or RNNs, as their foundational backbone.
And RNNs, by their fundamental mathematical nature, have to process data sequentially, word by word, left to right.
You cannot process the hidden state for the 50th word in a sequence until the network has completely finished processing the first 49. And in an engineering world where we just spend all this time optimizing matrix math to blast across parallel GPU cores, that sequential left-to-right requirement is a massive, frustrating bottleneck.
It totally defeats the purpose of the parallel hardware.
It severely caps how fast you can train these models, no matter how many GPUs you throw at the problem.
Which sets the stage for the most audacious question in modern computer science. What if you ripped the recurrent neural network out completely? What if you eliminated the left-to-right sequential processing entirely and processed every single word, every single position in the data simultaneously in parallel using only multi-headed attention?
That's the billion-dollar question.
That question would be answered in the famous 2017 paper, Attention is All You Need, which we will definitely have to tackle in a future deep dive. Thank you for joining us on this exploration into the architecture that changed everything. Keep questioning, keep optimizing, and we will catch you on the next one.
We started this deep dive by noting that human selective attention is a biological necessity. We have limited processing power. We literally have to filter out the background noise because our brains cannot attend to every sensory input at once.
Right.
But by moving to this massive parallelized scale dot product attention architecture, we are giving machines the ability to process all inputs simultaneously. They don't have to scan left to right. They attend to everything everywhere all at once. So the provocative thought I want to leave you with is this. By building this mechanism, are we actually mimicking human cognition? Or have we engineered an entirely alien form of parallel focus that completely bypasses the biological limitations that make human thought sequential in the first place?